Exponential functions have the characteristic that a variable lies in their exponent. That is, we have a base exponent situation, and the variable is in the exponent. So we have an exponential function. Now, there's a further restriction here of exponential functions, and that is that the base of these exponents has to be a positive number. And it's a number that also can't be equal to 1. We'll see why that's the case in just a little bit. Well, let's investigate the graphs of exponential functions like this. We'll start with this basic function and then make some changes and see how that changes the graph. Y is 2 to the x power. If I use a point plotting method, then I would build a table of values like this and I would plot a few points. Do notice, though, that as I'm building the table, if I go into the negative values, like for negative 2, you see if x is negative 2, then I put a negative 2 in place of this x. And that means that I have a misplaced base, so I end up with a fraction. I end up with 1 over 2 squared, or 1/4. That's how I arrived at this 1/4 situation here. Another interesting situation for this family of exponential functions is what happens when x takes on the value 0. See, since x is in the exponent, when x itself is 0, we have 2 to the 0 power, which is 1. All right, so that's going to be kind of a prevailing point in all of our exponential functions that are in that are configured in this way. Okay, plotting the points, constructing the graph, I get this graph, and let's talk about some characteristics that we see. We see a domain. The acceptable replacements for x would be all real numbers. We can see that graphically here, perhaps more clearly than we can from our function. The range would be positive values only. Notice that the graph lies entirely above the x-axis. Also, we may be noticing that the x-axis is an asymptote for this graph. That is, the graph is getting infinitely close to the x-axis as we go out in this direction. Notice also that this is a continuous function and it is continually increasing throughout its domain. That is, this graph is continually increasing. Others may not, but we'll see that as we go. All right, now let's change the base of the exponent. Let's consider g of x to be 4 to the x power and see what happens to the graph. We'll think of this as y is 4 to the x power. We build a table of values. Let's plot these points. 0 goes to 1. Same point as we had before. Again, that's a prevailing idea in this family of functions, that the point 0, 1 is going to be on the graph of the basic functions. All right, then 1 goes to 4. 2 goes to 16. Now 2 is off the graph. So that graph is coming down like this, rather sharply. And it kind of makes a turn right here. Then negative 1 goes to 1/4, and negative 2 goes to 1/16. So it's getting really close to that x-axis very quickly here. You see, so it has this kind of behavior. Now, from this, we're noticing that if this is the graph of 2 to the x, and this is the graph of 4 to the x, it seems to be the case that as the base of the exponent in exponential functions gets bigger and bigger, the graph rises more sharply and more sharply. And that is the case. And on the other hand, as this base gets smaller and smaller and sort of approaches 1, then the graph has the tendency to sort of lay down. For example, if I were constructing the graph of y equals 1.2 to the x power, then that graph might look something like this. See, it'll be a gently rising graph. So roughly 1.2 to the x power. All right, now let's consider what happens if we change things a little bit within the exponent. 2 to the negative x. 2 to the negative x. If I build a table of values, it would look like this. If x is 0, see, once again, we have 2 to the 0 or 1. That familiar point is still on the graph. If x is 1, though, we have negative 1 as the exponent on 2. Misplaced base, this becomes 1/2. If x is 2, we have negative 2. Misplaced base, 1 over 2 squared, 1/4. If x is negative 1 minus negative 1, that's 1. So 2 to the 1 power is 2, and so on. These are vaguely familiar coordinates here. Let's plot those points. 0 goes to 1. Then 1 goes to 1/2. 2 goes to 1/4. Negative 1 goes to 2. Negative 2 goes to 4. Negative 3 goes to 8. And the graph looks like this. You may notice that this is a reflection of our first graph. That is, here was our first graph, and if we reflect it in the y-axis, then it imprints right here. So this is 2 to the negative x power. Now, why is that happening? You know, we studied about reflections and transformations in a previous chapter, and if we rewrite this in a particular way, we'll see why that reflection took place. If f of x is 2 to the x power, then notice that f of negative x is 2 to the negative x power. You see? No wonder we have that reflection, because this is that idea that f of negative x gives us a reflection of the graph of f in the y-axis. So that's what's happening here. Now, another way to kind of analyze this situation is like this, that we can actually manipulate this a little bit. Now, I'm going to go back to the h function here. This h of x is 2 to the negative x. All right. And I can rewrite this as, now, misplaced base, I can think of this as 1 over 2 to the x power, or I can think of it as 1/2 to the x power like this. Now, we can actually think about this group of exponential functions, this one family, as having 2 branches to the family. One branch is where the base of the exponent is always x, let's say, but in one part of the family, one branch, the base is a number larger than 1. And in the other branch of the family, the base is between 0 and 1. And here's a situation where the base is between 0 and 1. And this is that circumstance where the graph continually decreases throughout its domain. And when the base is greater than 1, the graph increases throughout its domain. Okay, so we can either think of this part of the family of functions as taking on this kind of form with a negative exponent, or we can think of it as taking on this kind of form with a number as its base between 0 and 1. All right, kind of 2 ways to study the situation, really. Well, all of our ideas of transformations apply here with exponential functions. That is, if we take a basic function like f of x is 3 to the x power, and this is its graph, then we can imagine the graph of variations of f of x like this. Think of g of x as 3 to the x power minus 2. Now, we know 3 to the x power is this graph, and then this is just a group of vertical distances you see, and then we take those vertical distances and subtract 2, and this graph then will drop 2 on the coordinate plane. This is just f of x minus 2. You see, that's all there is to it. So we have, let's see, a drop from this familiar point down 1, 2, and the graph then looks like this. Another interesting thing that happens in these transformations sometimes, especially when we move up and down, is the notion that because we have an asymptote here at the x-axis, when we drop the graph down, the asymptote will drop down as well. So that asymptote will drop to this level. It just kind of follows the whole situation. Now, the other transformations occur in a similar way. Notice that the subtraction of 2 here occurred after the prevailing operation of exponentiation. Remember, when we studied this idea of transformations before, there was a prevailing operation, and our movement left and right or up and down was due to a calculation or an addition or subtraction either before or after that prevailing operation. If the addition or subtraction is after the prevailing operation, then the motion of the graph is up or down. If it's before the prevailing operation, there's a left or right movement. Here's an example of that situation. This is 3 to the x minus 2. You see, and remember, when we have that left-right movement, it's in a direction we don't expect. We see minus 2, actually the graph is going to move plus 2 on the coordinate plane. So the graph then will move to this position. Now notice I'm using as a reference point that point 0, 1. Is that point that's on many of the exponential function's graph. The graph doesn't actually go through the origin. The origin was a key point in many of our transformations from before. But here we're using the point 0, 1. Okay. Now, what about 3 to the negative x? 3 to the negative x. in function notation, this is nothing but f of negative x. You see, f of x was 3 to the x. This is f of negative x. This is that idea that we get that, that reflection in the y-axis. So the graph of this will be this. And another way to think about it is the notion of changing this into 1/3 to the x power. And when that base, in this form, when that base is between 0 and 1, we have a continually decreasing graph. Okay. K of x is negative 3 to the x power. Now, a couple of ways of analyzing this. We could actually use point plotting for all of these, by the way. But to think of it in terms of reflection, this is the negative of f of x. Remember that 3 to the x power had these vertical distances associated with it, and for k to the x, this is just the negative of those vertical distances. So we get a reflection then in our x-axis. And here we see that idea once again from our study before. So the graph looks like this. Here we put all the ideas together, and we have a number of changes here. Let's just pick them off one at a time. Start with the basic idea. All right, 3 to the x is just this graph. All right, then when we think about adding or subtracting before applying the prevailing operation of exponentiation here, then the movement is left or right in a direction we don't expect. We see +2, so the graph is going to move to the left 2. All right, so from this point's going to move to the left 2. Okay, then the graph will look like this. All right, then what about, let's apply one more transformation. Boom, the negative of this, the negative of those vertical distances, you see, will reflect in our x-axis. So that point moves, reflects down here, and the graph then looks like this. Okay, I don't want to imply that it's that the x-axis is an asymptote. I should let me just emphasize that it's not here by doing this. The only asymptote here, the only asymptote is this x-axis, and it's still the asymptote here because all we've done is we've reflected in the x-axis, so that asymptote is still in place. Okay, now let's add the 1. So we're at this point. Adding 1 after all of this business means we just lift the graph 1 on the coordinate plane. So that point comes to this point, you see, and the graph makes this curve, and the asymptote, which was at the x-axis, moves up to that level. Let's consider the graph of this function in several different ways. If we're thinking of the graph in terms of transformations, then we would think of 3 over 2 as 1.5. And 1.5 to the x power would be a relatively gently upward sloping graph going through 0, 1 on the coordinate plane. And then we think about it, the transformation of the adding of 2 before the prevailing operation. So that graph is going to shift to the left 2 places. All right, so that's one way to think about it. Another way would be to use a point plotting method, and that would mean we need to make a table of values. And to do that, we think of 3 over 2 as 1.5. If x is 0, then we would have 2 for the exponent, so we would have 1.5 squared, and evaluating that, 2.25. And then if x is 1, we would have, let's see, 1 plus 2 or 3 in the exponent, so 3 over 2 or 1.5 to the third power is 3.375, and so on. Okay, so now once these get a little bit complicated here, we need to use the calculator for evaluation purposes. And let's see what that would look like. If we were going to use the calculator to evaluate 3 over 2 to the 1 plus 2 exponent, then we would begin the process like this. We would open a parenthesis and enter 3 divided by 2, close parenthesis. All right, now we want the exponent on this 1.5. Now we could use 1.5, but I want to make sure we can do this for a lot of different kinds of more complicated problems than just this one. All right, then we would press the exponent button, and notice that since we have a binomial in the exponent, we would open a parenthesis and enter those 2 items in the exponent. So it would be 1 plus 2, close parenthesis, press enter, and we would get the value that we're looking for. Now, when performing this operation, if you're going to perform this operation over and over again, this is an awful lot of buttons to push just to evaluate this function for one particular value of x. And we wouldn't want to have to enter all of these things again for the next value of x. We can kind of streamline things a little bit by using a technique with the calculator where you press, after looking at this one, you would press second and enter. Second enter will give this back on display. This will be on the display. And then you can cursor back. You can cursor back to any item on here that you want to change. So we could cursor back, and right on top of the 1 we could put a 2 or a 3 or whatever. This was the position of x, remember? And so we can change the value of this entry and then press enter, and then it will evaluate the whole thing. And then once again, second enter will give this expression back, backtrack to that point, enter something else, and so on. All right, another way to evaluate the graph of the function is to use the graphing calculator. And let's do that now. And we're going to enter this onto the graphing calculator. The entry, by the way, follows a button sequence that's very similar to this. You know, all we're doing is replacing the 1 with an x, but we're opening parenthesis and closing at the same spots and so forth. Let's take a look at it. The function has been entered. Do notice that the exponent is contained within a parenthesis. If the parenthesis is left off, then it would effectively be y equals 3 over 2 to the x power, and then that amount plus 2. But here the plus 2 is part of the exponent. At any rate, here's what the graph looks like. And as expected, it is simply a shift 2 to the left of a graph that would go through the point 0, 1. If we were graphing 3 over 2 to the x power, it would go through this point, and this new graph is just shifted over 2 from that position. Pressing trace, we can verify one of those points that we had evaluated just a few moments ago. If I cursor over to where x is 1, we see that y is indeed 3.375. There is one very special and very useful exponential function, and it is special and useful because of its base, and its base is e. And it's symbolized with e, but it's actually a never-ending and never-repeating decimal. And we use this symbol for it because we don't want to write a lot of digits for its value. It has to be approximated in all cases, kind of like pi. You know, pi is a naturally occurring constant, and so is e. And in fact, e is probably more useful than pi is overall. At any rate, the value of e is approximately 2.71828 and so on. And in the calculator, we can find that value by doing this. Press the second button and then ln. The second function on natural log is e to the x power. And then press a 1 and press enter, and we will get its value. Okay. Now, when you do this, when you go through this process and you enter the 1, here's what you see on the calculator. When you press second ln, you are really pressing or accessing e to the x power. And the calculator will display e and then the exponent indicator, and then it will open parenthesis for you. So all you have to do is enter a 1. You don't even need to close the parenthesis. Press enter, and it will give this value. All right, and in a similar way, we can find e to any exponent using this idea. Well, it might be important for us to talk about where e comes from, or one reason why it exists, and so forth. What is this all about? Why does it appear in this study of exponential functions? Well, consider this notion. 2 to the x has this as its graph, 3 to the x has this as its graph. It kind of makes sense that e to the x will have its graph somewhere between these because the approximate value of e is 2.7. So it's 2.7 to the x power. And so its graph will be right in this neighborhood. Now why is that important? Well, consider the idea that a graph, and more particularly a point on a graph, indicates a rate of change. And you'll study all about that in calculus. But the rate of change corresponds with the slope of that graph at a particular point. And the slope of the graph is calculated using what's called a tangent line. A line which is tangent or barely touching at a particular point, like right here. The tangent line at that point would be this line. And the slope of this line at that point then would be the rate of change at that point. You see, the slope of the tangent line at a point. Now, that's kind of important in the study of exponential growth or decay. Now, when we talk about exponential growth and decay, and we'll get to problems like that in a little bit, but those kinds of problems have to do with population growth, you see, and we may be talking about an animal population that is growing at some rate. Well, that rate is modeled with an exponential function, it turns out. Also, radioactive decay is an area where we use exponential functions to emulate the situation. Now, often those problems begin with an analysis of some kind where the growth rate at time 0 is simply 1. You start with kind of a basis growth rate, and then you make your equations according to that or off of that. It's kind of one way to look at it. Now, the basis time is right here at this point. And it turns out, you see, that the slope of the tangent line, the growth rate for 2 to the x at this point, you see, imagine the tangent line at that point for that graph. Well, it would be a slope which is less than 1. All right? And the slope of the tangent line at this point for this other graph, for this graph, is a value a little bit greater than 1. So there must be a base on x, for x, such that the slope of the tangent line of the graph at that point is exactly 1. And it turns out that that base is e. That is, for the graph of e to the x, which is about like this, you see the slope of the tangent line at the point 0, 1 is exactly 1. Now, actually, I haven't drawn this graph anatomically correctly. It's the case that this graph is almost right on top of this one. You might try it on your calculator to see how very close it is. It's very, very close to the graph of 3 to the x power. Well, let's consider a function which has e as the base of an exponent. Let's see, how about f of x is 3e to this exponent? Now, to use a table of values, we would need to put in some integer values for x and evaluate for y. Well, if x is 0, let's see, if 0 is in place of x, then this becomes 0. E to the 0 power is 1. 3 times 1, 3. Okay, that's pretty easy. But for an x of 1, we would have to raise e to this exponent, you see, to the negative 0.2 power. Not an easy task. We need to use the calculator. So using the calculator, we would go through this button sequence. We would enter 3 and then e to the x. Now for e to the x, remember that's second ln for e to the x. Now the calculator display will automatically open this parenthesis, so we don't have to enter that, but I'm just putting it here for the completeness of this display. And then negative 0.2 times 1 close parenthesis, enter, and it'll give the value. It's approximately 2.5. And to evaluate for other values of x, we would again go through that idea of pressing second enter. You see in the display, the calculator will display this, and then change the value for the x that we're talking about. Now remember, the x here was 1. Just change that value, press enter, and boom, we have another value to put into our table. Well, let's look at this one on the graphing calculator. The equation has already been entered on the top line here, and notice the use of parentheses to contain this exponent. And it's always a good idea to use parentheses to contain complicated exponents, and the opening of the parenthesis is actually an automatic on the TI-83. The situation also applies when evaluating an expression for use in a table of values. Let's look at that situation a little bit, and I want to show you more clearly that technique that I was talking to you about. Press second and then the mode button, and it'll give us a clear main screen. If we press, let's see, it was 3, then e to the negative 0.2. Now we're going to multiply times, it was the x in this position. We'll replace x with 1 and then press enter. So here is f of 1 if we're thinking of it as a function. And then if we want to find f of 2, we would press second and enter. And you see what it'll do is just repeat the first line. It'll take this line that we entered and it'll repeat it. And all we have to do is backspace one time, enter a 2 and press enter, and then it'll evaluate for f of 2. So in doing this, we save a lot of entry steps in the process. Well, let's go back to y equals and look at our graph. Now, another thing that's important to realize about a graph like this, or an equation that looks somewhat complicated, and in trying to predict its graph, is we can investigate its graph like this. Now, I'm going to take this graph offline by pressing enter here with the icon blinking over the equal sign, and I'll press enter for each of these with the icon over the equal sign to access them. And we're going to look at their graphs in a moment. But what I've done here in this progression of equations is I've simply taken a most degenerate form of the equation that we have. This looks somewhat complicated. So I simply wrote down the equation for e to the x power. All right, we know what that pretty much looks like. We can kind of predict this transformation. And then I added one little nuance, the coefficient of the x here for this one, and then I popped in the coefficient of 3. And what we want to notice is how the graph changes for each one of these little changes in the equation. Well, let's see. Here's the graph of e to the x power. Now, e to the negative x is a reflection in the y-axis. Now, here's what happens when we just put that coefficient of 0.2 on the x in the exponent. Now, it's important to understand what happened here between this graph and this graph. You see, we can think of this as a transformation from that. If we realize that when we multiply by that x by a coefficient, which is a fraction, a number between 0 and 1, it'll simply cause the graph to stretch this way. That's what's happening. Now, it looks like the same kind of transformation that we get when we multiply by an outside coefficient. But it's not quite the same. Looks similar, but it's not quite the same. Now, in going from this graph to the graph of the equation we were talking about, we are multiplying by 3, which means that every vertical distance on this graph is multiplied times 3. Here's the point 0, 1. That vertical distance is a distance of 1, and the vertical distance on our graph is a distance of 3. And for a vertical distance, for example, right here, multiplying times 3, we would get that vertical distance for the graph that we are talking about. So every vertical distance is multiplied times 3. At any rate, the point is that we can take rather complicated equations and learn a lot about how their graphs are going to behave just by taking progressively more complicated forms of the equation from some degenerate form.